Hey guys, welcome to lecture number 9.1. I think it's a continuation of the last lecture. Well, unfortunately, I said at the beginning that it's going to be like 1 hour and 20 minutes, but at the end it's going to be just 1 hour. I would like to continue with our discussion from last time when we start talking about matrices of order n, about eigenvalues, eigenvectors, and even we talked about the rank of a matrix. So let's get started. Let's do some problems because I didn't have time to do many problems last time. So if you look, the last problem that we did last time was this one here. If you look at it, it's if and only if, and we proved that we did it in two ways. And I would like you to take into account these Newton's identities. In fact, we'll do another problem today using this. So we proved this. So from last time, keep in mind that, the other implication, I'll leave it to you as an exercise. So the other implication. So the other implication is, what is it, from right to left? Is an exercise for you. So I'll leave it to you as an exercise. And I would like to do a problem. So keep in mind this. Always you can prove something about the matrix, that the matrix is in fact nilpotent, whatever that means, we'll see immediately, if and only if the traces all the way up to the size of the matrix are 0. And that we have used this in problems that we did last week, right, for matrices of sizes 2 and 3. So without even saying this, because we played around with Cayley-Hamilton and so on. All right. Now I want to do the following problem. So this is problem number 2. Okay. So problem 2 says the following. If I have a matrix, because I want to settle this with complex entries, then if A is nilpotent, which means that there exists a K such that A to the power K is ON, right? Then A to the N is 0N. So keep that in mind, right? We did this for order 2. We did this for order 3. Now let's see for order N. And again, the same thing will apply. So solution. We will have in mind to use the Cayley-Hamilton, this time for matrices of size n. So we apply the Cayley-Hamilton equality. And what do I mean by that? So the Cayley-Hamilton, we can write it in this way. So we can write this as A to the N. Okay, let me write it in this way. So it's A to the power N plus, let's say, another coefficient A to the AN, okay, times A to the power N minus 1 plus A sub N minus 1 times A to the power N minus 2. And we keep going all the way to A2 times A plus A1 times the identity. This will be the null matrix. So we know this. This is the Cayley-Hamilton. All right. All right. So now what we're going to do. So we want to show that a to the power n is 0n. And we know that there exists a k such that a to the power k is the null matrix. Well, if k is greater than n, let's point out this remark. Wait. If in fact, if k is less than n, right? Is it obvious? It is obvious that well, right, since a to the k is less than n, you just multiply by a till you get to n, right? Because it's 0. It's multiplied by the matrix 0. It's obvious that at some point you'll reach all the way to the size of the matrix, right? So it will be a to the n. But now if now assume that k is greater than n, and we want to show that if a to the k is 0, then and a to the power k is the null matrix. And now we have to show that a to the n is 0. So what are we going to do? So now let's choose. So choose k to be minimal, to be the minimal with okay, such that a to the power k minus 1 is not 0 and a to the power k is 0n. All right, so we choose this to be minimal. And now what we're going to do, let's call this star here. Now what we're going to do, we're going to multiply this Cayley-Hamilton equality, this with, we're going to multiply by the a to the power k minus 1. So multiply star by a to the power k minus 1. Okay, so what we're going to do, because a to the power k minus 1 is not the null matrix, and we have, so what do we have? We have that a1 times a to the power k minus 1 plus a2 times a to the power k plus all the way plus an times a to the power k plus n minus 2, right? Plus, then the last one will be a to the power k plus n minus 1. This will be the null matrix. So what does it mean? Well, we know that all these, since all these, since a to the k is equal to a to the k plus 1, all the way to a to the power k plus n minus 1 is the null. Since all these are equal to the null matrix, it follows that let's see, what does it follow? It follows that a1 times times a to the power k minus 1 is 0, right? So what does this imply? Since a to the power k minus 1 is not the null matrix, it follows that a1 is 0. So that is the only option we have here, right? So a1 will be 0. And now we're going to do the same thing. So we repeat the procedure. So repeating this procedure, let's say for by multiplying star with, this time I'm going to multiply it by a to the power k minus 2. We obtain a2 will be 0, and so on. And so on. So this will imply that all of them, so finally, we obtain that all these numbers, a1 is the same as a2, and all the way are equal to all the way to an equals 0. So a to the power n is the null matrix. That's it. Keep this in mind. You can use this as a lemma. Is it clear for everybody? So you just repeat the procedure. We've done this in the case of n equals 2 and n equals 3. All right. Now, let's do the following problem. In fact, problem 3. Which says the following, right? Let AB be two n by n matrices with complex entries, and we define the Lie bracket or the additive commutator. So the bracket AB is AB minus BA, right? So this is the additive commutator. I've talked about it in previous videos. And now show that if the bracket AB is A, then A is nilpotent. Okay, look at this problem a bit. Think about it for a couple of minutes. So let's see. What do you know about the commutator? Maybe we could use, we have in plan to use problem 1. So we want to use problem 1. And keep in mind what problem 1 said. It says that if the trace of a to the power k is 0, then a is nilpotent. That's what it says, right? So we need to compute the traces of all these brackets to the power k for all k from 1, 2, and n. If all these traces are 0, then yes, by problem 1, I can conclude that A is nilpotent. So let's see. For k equals 1, what do we have? Trace of the bracket AB, and if you look at the bracket, is nothing else. Trace of AB minus BA. And this is trace of AB minus trace of BA, but this is 0. All right, so this is 0. Now let's see for k equals 2. Trace of AB squared bracket. But keep in mind that AB, so this guy is A. So this would be equal to the trace of, let's put it like this, AB bracket times A, so that I don't need to expand and compute the squares there. I think it's much easier to do it this way, right? And this would be the trace. If you look at it, this is AB. Now we can write a bracket because the computations are easier this way. So this would be, and now we can multiply the trace of ABA minus BA squared, or BAA, let's put it like this, which is the trace of ABA minus the trace of BAA. But now let's use this property again. So we know that the trace of XY is the same as trace of YX. And now we just take X to be A and Y to be BA, right? And this will give us, if you look at this, this will give us the trace will be 0, right? Now let's see for k equals 3. Let's see one more. Trace of AB bracket cubed. But again, the same thing happens here. I can do this trick. I know that AB bracket is A, so I'm just going to leave it one bracket, AB bracket times A squared. And I'm going to do the same thing. So this would be the trace of AB minus BA times A squared. And I'm just going to multiply. So this would be the trace of ABA squared minus BA A squared. Let's put it like this. And again, the trace of ABA squared. So this would be, this is equal to the trace of ABA squared minus the trace of BA A squared. Is this equal to 0? Well, just apply the property above about the trace. You can just take, so again, take here, so trace of XY is the same as trace of YX. And now you're just going to take here X to be, let's see. Why is this true? We'll take X to be A and Y to be BA squared. And I think that's, again, and this will give you 0. And now you can keep going. Let's see for generally, so more generally, I just showed you how it works for k small. But now more generally, we have the trace of the bracket AB bracket the power k. And I'm going to do the same trick now. This will be the trace of AB bracket times a to the power k minus 1, right? Keep in mind that AB bracket is a. So this would be the trace of, so I'm just mimicking everything that I've done here, previously did. So AB minus BA times a to the power k minus 1, which will be the trace of, and now let's multiply things here, trace of AB a to the power k minus 1 minus BA a to the power k minus 1, which is again the trace of AB a to the power k minus 1 minus the trace of BA a to the power k minus 1. Now the question to you, is this guy equal to 0? Well, it's the same thing. It will be equal to 0. I will leave this to you to figure this one out, but it's the same thing as I previously did here. So now for all case, so the trace of the bracket is 0 for all k from 1 to n, right? So by problem 1, it follows that the bracket AB is nilpotent, but the bracket is equal to A is nilpotent. And that's it. That's the end of the problem. Very nice problem, right? Is it clear for everybody what we did here? Chris, Caroline, Abby?
Yeah, I think it makes sense.
Oh, wait, just a second. Wait, I forgot about the, it's clear, right?
Yeah, yes, it is clear.
Okay. All right. Now let me do another problem. Something relating the rank of a matrix, since we talked about this, but I want to do it. And the problem says the following. So problem 4. I know these are a bit harder problems. You haven't seen this in your undergraduate in any other course you have taken. Definitely not. This was international mathematical competition. There's a worldwide Putnam. I even participated in this competition back in the day when I was an undergraduate. And this was in 2000, this problem given. And the problem says the following: let AB be two matrices with complex entries such that, and now I'm going to say something about the rank, such that the rank of the bracket again is 1, where the bracket here is again the additive commutator. So this is AB minus BA, right? Show that AB minus BA squared is the null matrix. By the way, I have a question. Do you like my background? Stay like this. Can you see it?
Is that Pittsburgh? Is
Yes,
that Pittsburgh?
Yeah, Pittsburgh, yeah. Pittsburgh,
Yeah,
Pennsylvania. Cool. You like the skyline. There are, it's called the city of, usually it's called the Steel City, but it's also called the city of bridges. It has like more bridges than Venice, like 400 and something. So it's yeah, this is where I spend my my last 6 years of my life before I came to Lubbock. All right. Now let's see. So how should we approach this? We have the following lemma here. And I think the problem will follow immediately. So we show the following lemma. And the lemma says the following, that if, let me write it with a different color. If I have a matrix X and with complex entries and n by n matrix, right? Such that the rank of this matrix is less than 1, then we have the following. We can write the matrix, then x squared is nothing else than just the trace of x times x. Wow, that's a very important thing. And this happens if the rank of A is less than 1. Then this happens. So let's prove this lemma. And I want you to keep in mind proof of the lemma. Right. So let's see. So since matrix has rank 1, so any matrix of rank at most 1, okay, let me write like this. Any matrix X with rank of X less or equal than 1 can be written as so we can write X in the following way as the product of so it's UV transpose, where UV are column vectors. This is actually, you can do this even in a standard linear algebra course. I think I've done it. And now let's compute x squared. Now x squared, and you will see how we compute this. If we compute this, so this would be UV transpose, but now this guy will be UV transpose U times V transpose. But this guy here will be nothing else than just a trace of X, right? So this is the trace of X, right? If you write, just imagine, just write explicitly U as U1, U2, UN, and V will, well, it's a row, and then your column, when you multiply, then you'll see exactly this. And well, this would be nothing else than just the trace is a scalar, so it would be the trace of X times UV transpose, but UV transpose is X, so it would be the trace of X times X. And the proof of the lemma ends here. So that's the proof of the lemma. Okay. Now let's see our problem. Well, at this point, you just take X to be, so take X. So going back to the problem, just take X to be the bracket, right, the additive commutator. AB minus BA. And we have, and we get, let's see, what do we get? We get that by the lemma. Right, because we know, look at the statement of the problem, we know that the rank is, look here, the rank is actually 1, so I can apply the lemma, so it follows that AB squared, so the bracket squared, so AB minus BA, everything squared, so this is the bracket squared, will be nothing else than just the trace of the bracket AB times the bracket. Right, but this guy here, the trace, this guy here is 0, right? So this will give us nothing else than just the null matrix, and that's it. That's the problem. So the lemma basically just destroys the problem immediately. So is it clear for everybody, the problem and the lemma as well? All right, now I think I'd like to do another problem using the rank of a matrix, and I think I gave you this inequality of Sylvester. So problem number 3, I think it is. Number 5, sorry. I think this was some kind of Romanian Olympiad anyway. Back in 2006, whatever, which says the following: if n and p, so if I have two positive integers are positive integers, well, greater or equal than 2, such that a to the power p plus 1 equals a, then show that the rank of a plus the rank of the identity minus a to the power p is n. All right. So let's see. Remember, we did something. Let me remind you that last lecture. So last lecture, we discussed about these two inequalities. The following rank inequalities. And let me mention them again. So we said that the rank is subadditive, so rank of x plus y is less or equal than rank of x plus rank of y, right? And the second one, it was a Sylvester inequality, which says that, what does it say? It says that rank of x plus rank of y minus n is less or equal than rank of xy. So this is Sylvester's inequality. Or, well, the first one you can actually, I think I've put the first one as an exam problem. Well, of course, I put some hints to help, but the first one was an exam problem in my linear algebra course. It's pretty standard if you. And now let's use these two. For this problem. In fact, I want you to think of it. So look at these two inequalities and try to use it for your problem. And also keep in mind that we have this relation here. So I know this, I want to prove this. So let's see, how should we approach this? Well, by Sylvester's inequality, so let's apply this. By Sylvester's inequality, oops. We have the following. So let's see, what do we have by Sylvester's inequality? We have that. Let's see. So we have that rank of, keep in mind what we have to prove. So rank of A plus rank of the identity minus A to the power P. This guy is less or equal than N plus rank of the product, rank of A times the identity minus A to the power P. So this would give us N plus rank of A minus A to the power P plus 1. But these two are, this is 0. So this will be a rank of, which was 0, so it's N. So I know that this is less or equal than N, but I have to show it's actually N. All right, so I know that is less or equal. Now I want to show that is greater or equal, and then it will follow that they're equal. Now, on the other hand, we have that, let's see, what do we have? On the other hand, we have that rank of A plus rank of identity minus A to the power P, right? This will be greater or equal than rank of A to the power P, right? Because the rank of A is greater or equal than rank of A to the power P plus the rank of the identity minus A to the power P. But now, by applying the first inequality, this will be greater or equal than rank of A to the power P plus the identity minus A to the power P. And this will be equal to rank of the identity, which is N. Well, guess what? Look what we proved. We proved that this guy is less than N. We proved that the same guy is greater or equal than N. So by these two, therefore, the rank of A plus the rank of the identity minus A to the power P is N. And that's it. You see, it was just a combination of these two inequalities, Sylvester and this, that the fact that the rank is subadditive, right? Anyway, this is just one application. There are plenty of other applications. Now let me do another problem. Yeah, this is a very nice problem, though. I would like to do it. I hope I'll have some time. So problem number 6. Says the following. Let AB be 2 n-by-n matrices such that we have this condition, a squared plus b squared is 2 times ab. Now, show that, so the first part, show that the matrix, basically the bracket, again, AB minus BA, is not invertible. And the second one, if the rank okay, let me write like this. If the rank of A minus B is 1, then AB is the same as BA. So let's look at this problem. And now, this problem is not it's a bit tricky. It's a tricky problem where there are two ways of doing this. First, what we need to do is we need to rewrite this condition in two ways. So the condition a squared plus b squared equals 2ab can be written as, and let me write this with a different color. So we can write this as the following: a minus b, everything squared. So this is a squared plus b squared, so, but this would be ab minus ba. Let's call this 1. And on the other hand, a times a minus b, we can is a minus b times b. Right? Okay. So now we have these two conditions. Let's call this 2. And now let's assume, so what does it mean for a matrix to be not invertible? It means that the determinant is 0, right? It's singular, right? So let's assume that, so assume by contradiction that the matrix, so the commutator, right, the bracket, is singular, is non-singular, sorry. Is non-singular. Okay, so this means that, that the matrix, well, since by relation 1, if you look at it, this means that A minus B is non-singular as well, right? So this means that we can, so the inverse exists. A minus B inverse exists, right? The determinant non-singular means that it's invertible. So the determinant is different than 0. All right, great. Now we can multiply by it. So let's multiply the second one. So multiplying 2 by the inverse of A minus B. And we're going to multiply this to the left. And we get the following. So let's see, we look at relation 2, we multiply by A minus B to the inverse to the left. So we get A minus B inverse times A minus B is equal to A minus B inverse times A minus B times B. But this guy here, if you look at it, is the identity, right? So this is nothing else than just B. Right? Or okay. But also if you all right, so we have here, but now if we look at A minus B, but A minus B, if we look at this guy, is nothing other than just A minus B inverse times A minus B times B. Okay? Or if you want, we can multiply by A minus B so let's see, what can we do here? So we want to multiply by A minus B inverse. So we can multiply it to the so multiplying by A minus B inverse, right? Let me see. I think I've done something wrong here. I wrote this wrong. Jesus. It's B. Made a mistake here. So this is A minus B inverse times A minus B, and now it's clear. So we multiply by A minus B inverse to the right. Let's put the star to the right of star. And we get, let's see, we get A minus B inverse times A minus B is the same as way to the right. Jesus, what am I writing here? A minus B times A minus B inverse is the same as A times A minus B inverse minus A minus B inverse times A times A minus B times A minus B inverse. All right, this guy here will be the identities. So this or equivalently, we have that the identity IN, so again, this is the identity, is the same as A times A minus B inverse minus A minus B inverse times A. And now guess what? I'm going to take the trace, so apply the trace. So by applying the trace, we get N, which is the trace of the identity, is the same as the trace of this guy, A times A minus B inverse, minus, okay, let me write this with minus the trace. So I'm using the linearity of the trace of A minus B inverse times A. But this guy will give you, well, if you see they commute, it will give you 0, so which is a contradiction. So where did the contradiction come from? From my assumption. Look, it comes from here. So we assume by contradiction that this is not singular. So therefore, the bracket is singular. So this implies that, right? Now the second part, I will leave it to you. Use the fact that that if the rank of X is less or equal than 1, then, so we just proved that X squared is the trace of X times X. All right, guys, I think I'm going to stop here. Well, I will do some other problems in linear algebra. Maybe there will be another recitation. So, and also next week, again, we'll continue with linear algebra. I'll show you some special things in linear algebra, such as Schur's theorem, Jordan canonical form, well, Jordan, not Jordan, and some other crazy stuff in linear algebra about linear transformations and so on. Okay, thank you very much.